Okay, so in this short video, I'm going to give a short explanation about radioactive decay scheme. It is a graphical representation about the decay of a nucleus from an excited state to the stable state or to the ground state. Okay, so before that, okay, let's I want to show you the nuclide charts. Okay, so uh, so you Google IAEA nuclide chart. Okay, and you go to the live charts of nuclides. So this is so far the most comprehensive online database for radionuclide for nuclides. Okay, not only radionuclide but nuclides as well. Okay, by saying nuclides, I mean the stable state nuclide. Okay, so if you can see, this is like the map of Honshu of Japan, but it is not the map of Japan. Okay, this is the on the on the x on the horizontal direction is the number of neutron. Okay, so the more you go to the right means the number of neutron increase. Okay, and the x and the y-axis or the vertical direction, okay, is the atomic number or the proton number or the z number. Okay, if you can see, okay, if you can see, let me zoom in. Okay, so now I'm at the bottom. Okay, I'm at the bottom of one of the column. Okay, and this column correspond to the neutron number 56. Okay, so if I go upward, I move my cursor upward, you can see the z or the atomic number is increasing. Okay, so now z is 38, z is 39, 40, 41, 42. Okay, until 54. Okay, if I select one z, okay, let's say this 42, okay, and I move to the right, okay, you can see that the number, the n, okay, the n is increasing, the n at the top. Okay, if you see the in the box at the top, and now 50, now 51 to 53, okay, so on and so on until the end of the row. Okay, so the row is constant z number, and the column is the constant neutron number. Okay, and okay, what you can see in the plot is if it is in black in color, it is stable nuclide. Okay, for example, this is hydrogen number 1. Okay, hydrogen 2 is stable. Helium, okay, you go as much as you want. So nuclide in black is a stable nuclide. Okay, and other than that, okay, if under the stability region, under the island of stability, or in blue, in the light blue color, that is the proton rich nuclides. Okay, so it will decay either by electron capture or beta plus decay. Oh no, beta minus decay. So this is the neutron rich nuclide. I'm sorry. So light blue is neutron rich nuclides. Okay, because if you go to the right, meaning that the number of neutron increase. Okay, so this is neutron rich nuclide. So so the nuclide decays according to beta minus decay. Okay, and in the green, so nuclides plotted in green color is are the proton rich nuclide. Okay, meaning that if you go upwards, okay, the number of proton increase, okay, or the number of z increase. So meaning that's the those are the proton rich nuclide. So they decay. So they will decay according to hadron capture or beta plus decay. Okay, and if you go okay, after, okay, mostly after z greater than uh, z greater than I think 80 something. Okay. This one. Okay. If z greater than 80 something, okay, you can find that uh, the you will find heavy nuclides, okay, which decay according to alpha decay. Okay, we discussed that in our previous lecture. Okay. So if you let's say, okay, so this that's all I think that I want to say for the feature of this life chart nuclides. And next, okay, so if you, let's say, if you interested to know about let's say uh, let's say oxygen, oxygen 16. Oxygen 17, nitrogen. Uh, Let me zoom it. Z equal to 8. Okay, there you go. There's oxygen 16. Okay, so oxygen 16 is a stable nuclide. Okay, so stable means that it is at the ground state. So the energy the energy, the state of the energy is zero. Okay, so it's stable, and the abundance is 99.757%. This the abundance. I think you learned that in 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 chemistry during your previous study, I think. Okay. So most of oxygen exists in nature, okay, is oxygen 16 with 99.757%. So that's the abundance. And then the rest are, I think this is too much if I want to go one by one. Okay, but the important one, I think, that you learned previously in this class is the binding energy per nucleon, okay? The atomic mass in micro AMU, okay, mass excess and mass excess as well. Okay, so that's stable, an example of stable nuclide. Okay, if for an unstable nuclide, okay, for example, let's say cesium, for example, there are many, from the chart itself. From this chart itself, you can see the amount of unstable nuclide are tremendous. Okay? But what I want to show now, the common radioactive material that can be found in laboratory, which is one of it is cesium 137. So if you Google cesium 137 and you look at images, okay, you can find a chart like this, a scheme like this, okay, like this one, or this one. Okay, so let's look at this diagram. Okay, so this is what it is called a decay scheme. The decay scheme for cesium 137. Okay, 55 is the atomic number. Okay, 137 is the mass number. Okay, 30.17 is the half life. Yeah, after this, you will look into half life. So half life, 30.17. A means annual, so year. So mean that cesium, if you have 100 gram cesium 137, okay, then you have to wait for about 30 years, okay. The 100 gram of cesium 137 becoming 50 gram. Okay, so this is the half life of it. Okay. So it decays according to mostly, okay, the dominant decay mode, okay, with 94.6% is to the beta minus decay, okay, but not directly to the ground state barium 137. Okay. So 94.6% will lead to a metastable barium 137. Okay, M indicates the metastable. So that M is stand for metastable. So meaning that cesium, nuclide cesium, already changed to barium. Okay, proton increase to 1. Okay, in beta minus decay. Okay, too much neutron, so neutron is changed to 1 proton. Okay, so the element is the element changed from cesium to barium. Okay, but not yet a stable state or ground state barium. Okay, so uh, it is at a metastable state. Okay, and only 5.4%. Okay, only 5.4% will directly lead to the stable barium 137. Okay, so uh, the 7/2 plus here is the spin, okay, spin and parity of this cesium 137. This one 11/2 is 11/2 minus is the spin number for barium 137 at excited state. Okay, and the ground state barium 137 has the spin 3/2 plus. Okay, and then and barium, okay, barium, the metastable barium 137, okay, has the half life of 2.55 minutes. Okay, decaying to the stable barium 137. Okay, according to releasing a gamma decay. So this gamma decay has energy of 0.6 617 mega electron volts. Okay. So if you sum up 0.5120 with 0.6617, okay, you will get 1.174 mega electron volts. Okay, so the energy difference between the stable states barium 137 to the excited state or the unstable state cesium 137 is 1.74 mega electron volts. Okay. So we can cross check the cesium 137, okay, on the actually I'm a little worried whether I'm recording the video or not. Okay, so let's cross check it with this live chart. Okay, so 137 cesium. Okay, you press enter, and this is the cesium 137. Okay, if you click on it. Okay, go to the decay radiation. Okay, so beta minus decay. Okay, so beta minus decay. Half-life is 30.08 year, but here reported 30.17 year. So this one is reported by somebody else. This one also reported by somebody else. So their measurement a bit slightly different, but about 30 years. Okay. So 100% beta minus decay. Okay. So like 100% mean, so both this line and this line, okay, account for the 100% of beta minus decay in reported here. Okay. So cesium, okay, decay to metastable barium. Okay, and after that the metastable barium, okay, will decay to stable barium. Where is stable barium? Stable barium is here, ground state. Okay, here. So energy is 0. Okay, and then what else? So there are many value reported. There are many possible value reported. Meaning that the state of barium 137 is not only is not only one state. Okay, you can have many possible state. Okay, different in slightly in energy level as well as the nuclear spin. Okay. Let's see about this scheme plot. Okay. Not barium, cesium 137 that we are talking about right now. So cesium 137. There are many. So that like I said here at the level, there are many possible energy level. Okay, but the one that we seen here is the most dominant one. Okay, so so the one that we see here is not this one. Okay, not here. So what I conclude, what we conclude here is that the commonly used decay scheme for cesium 137 is the dominant one. Okay, so this one is this is the this is more detailed, okay, considering the all possible state of cesium 137. Okay, so is it beta minus decay? Yes, it is beta minus decay within here. But if I zoom out the chart, is disabled. Okay, cesium 137 is here, so it is beta minus decay. So next the next nuclide that also popular that can be found in most laboratory is cobalt 60. Okay, so cobalt 60. Okay, so cobalt 60 also cobalt 60 also beta minus decay. Okay, beta minus decay, but I think the decay scheme is more complex than cesium-137. Let's check it. Okay, so there are many metastable. There are two metastable states. Nickel metastable state for nickel 60. Okay, so which is one way of decay is releasing 0. Let's open the image in new tab. Okay, so 99.88% cobalt 60 decay to nickel 60. Okay, metastable nickel 60. Releasing 0.31 mega electron volt of electron. Okay, and the rest, which is 0.12%, is to the slightly is lower than the first one. Okay, lower than the first one by 1.1732 mega electron volts. Okay, at this second metastable state. Okay, and the half-life. Okay, half-life of cobalt 60 is about 5 years. So this one, this image doesn't state the half-life of the metastable nickel. Okay, so you get two types of energy of gamma ray. Okay, so the first one is from this state to this state. The second one is from this state to this state, to the ground state. Okay, so let's check the live chart. Cobalt 60. Okay, so first is beta minus decay. Okay, this one. So 100% beta minus decay. Okay, so let's consider these two pathway. Okay, the second one is this one, the gamma decay. So this first gamma decay, and the second gamma decay. Okay, so this is the first gamma decay to the second gamma decay. Okay, so here we have the half-life. Okay, 10 minutes. Okay, both occurs. Both half-life is 10 minutes. Okay, so this one is 10 minutes, this one also 10 minutes. Okay, So the rest, I think, if you have nuclide in interest, you can explore this chart. Okay, there are many data actually, which even myself haven't learned them before. Yeah, this is too much, I think. Okay, for the applied physics course, I think these all are too much. Okay, so I think that is that cover all the subchapter 4.2 relative decay scheme. Okay, okay. Before I forget. Okay, other than alpha electron capture, beta plus and beta minus decay, you can see there are SF, P and N. Okay, SF is spontaneous fission. Okay, there are some nucleus which spontaneously undergo fission reaction. Okay, and N stand for the neutron emission, and P is the proton emission. Okay, but the uh, the phenomena is not common. Okay, it's special. There are those are special phenomena, and I think naturally occurring radionuclides. Okay, uh, don't decay by the spontaneous uh, fission or proton emission or even neutron emission. Okay, so those the special case special decay modes only occurs with artificially made radionuclides. So that's all for the subchapter 4.2. Thank you.